Okay, so this was the plan of the talk as I envisaged it last night. And what I had in mind is to spend 10 minutes on this period. Was this thing that Natalia gave me? Thanks. And, okay. So this is just supposed to be explaining what is meant by logic, just on the most basic level, formulas and so on, and how you can use that as a tool to look at geometry, as it has been for a long time. The second part was supposed to be about something that happened in the 80s, started happening in the 80s, that we suddenly started realizing, mostly because of work of Zilber's, that it's not just something that you can do if you choose to. If you do logic, you must look at geometry. There's an essential embedding of, let's say, for example, of algebraic geometry within the most basic questions purely about logic. And some things that came out of that. And then I wanted to go back, and that's maybe 10, 15 minutes, and then I wanted to go back to talk about the real engine which is making everything work. It's quite easy to talk about somehow at a high level about connections to geometry, but when you actually prove something, there's some machinery behind it, and in our case it's called stability, and it's really the hardest thing to explain because it does not look like geometry, it does not look like topology, it looks like something else, but I was hoping to make an effort and explain that for 10 minutes, and well, the last part was supposed to be applications, but somehow I knew that the 10 plus 10 plus 10 minutes would probably amount to more than 45, and I would never get there. But I thought it wasn't very important because somehow the most important thing is to show the machinery. But then this morning, there was this very sweet provocation by Maxim, who said that there are no applications. So this made me change my mind a little bit and think, well, maybe I'll start by talking about a few of the applications and then explain the machinery that leads to them. And the truth is that what Maxim said was absolutely correct. There are to within 5 decimal places, it's absolutely right that there are no applications of logic to geometry. You can know geometry extremely well without being aware of a single application. I will talk about one or two or three. Well, there's a discrete number of exceptions, but it's true that there's a measure zero of applications. There's not a continuous stream. There's some points, but it's true for a non-trivial reason, and I would like to explain the reason and also the reason for the hopes that the technology will develop in the future to allow also a continuous spectrum later. So let me start with talking about the applications, but just to have a few words behind us. Okay, so logic does not start with any kind of given object. It does not start with the points, right? Usually today we construct something, let's say a geometry, by starting with the points. And then we say, okay, here are the points, and here's the topology, and here are the various structures, and then here's what we don't care about, and what's left is the geometry. And in logic, you don't look at the points. You start with looking at the relations, at the language that describes them. So if you're talking about, I don't know, planar geometry, you just say, well, I have two kinds of things, points and lines. These are called sorts. And I have some relations between them, so maybe just the relation, a point lies on a line, but I'm not actually given a set of points. I'm just given the language with which I can talk about it. And then I form expressions to discuss these points and lines. So I might say, for example, the two lines are parallel. So I can say that using a limited number of symbols. I say it's not the case that there exists a point which is incident to both these lines. And okay, so you just have these very few symbols, and the funny thing is that essentially anything you want in mathematics can be expressed using these symbols if you give yourselves the right kinds of objects to talk about in advance. But these are the logical symbols that are needed. So they're very familiar for all. There exists and, or, negation, and equality. Okay, so here, this was a formula. It's something that states a property of lines, so it cuts out what is called a definable subset. It's a set of lines from among the plane that you form by the set of all-ordered pair of lines, right? Those lines that have a point in common, that intersect. You have things which are formally of the same nature, but actually they play a very different role, which are sentences, namely things which are not about any particular object, but about the whole geometry, which are either true or false. So an example is the parallel axiom. I didn't write it down in detail, but it says that, well, you know what it says, and you can write it down in this language. Okay, a theory is a set of sentences which is closed under logical deduction. So there is some well-defined notion of logical deduction. Okay, this is the kind of, so this is in the background. This is the kind of thing that you start with. Yeah, the first theorem in the subject is the model existence theorem, which we call the completeness theorem, but it refers to the completeness of something which I'm not even talking about, namely the deductive system. That any consistent theory has a model. And I think it's quite common that the first applications of theorems come a long time before the theorem is stated or proved. Yes, namely there exists a structure consisting of points, of elements, and the relations are something that you can, some sets of ordered pairs or something like that. Yeah, there actually exists a collection of points and a collection of lines. So I think the first application of this theorem is something that Gromov in fact mentioned kind of in his first talk, namely the existence of hyperbolic geometry. So if you remember the motivation for this kind of question, there are several motivations, one of which is maybe spherical geometry was known, maybe people thought about surfaces, but the main motivation was a completely logical question of whether one axiom follows from another axiom. And the first construction was also a logical construction. Gauss tried the geometric construction, and as you said, didn't publish it, and I think no such construction was published until much, much later in the century, because it's harder to, in that case, logic came first. It was harder to build a model of hyperbolic geometry by actually naming points and distance relations between them. And Lobachevsky, who was completely accepted to have constructed hyperbolic geometry, as far as I understand, he did it using Gödel's theorem. Namely, he said, okay, well, here are these axioms. Now I'm going to check that they're consistent. I'm going to make all possible deductions from them. And if they're consistent, then we just assume that they have a model. And everybody accepted this. Poincaré explicitly accepted it. He said that the only question was whether, in fact, Lobachevsky had made all possible deductions. But he accepted that there's no need to prove the completeness theorem. Now, in fact, there is a need, because this theorem applies to geometric objects. It's totally false by another theorem of Gödel's. It's totally false for the mode of existence that have numbers or functions. You can come up quite easily with partial differential, well, anyway, I don't know. You can come up with partial differential equations such that it's completely consistent that they have a solution. You cannot deduce a contradiction from it, but they have none. But it's not true for geometry. There's something about geometry that fits very well with the axiomatic system. And for that, it's true that consistent things of that type exist. Okay. When did I start?
6 minutes ago.
6 minutes ago. So, but it's better to remember the time. Okay. Okay, fine. Yeah, I mean, these... Well, I'll mention some other applications which came later, after all, I think. So one famous one is the Ax-Kochen theorem. And it doesn't actually matter what it says. It says that something, some sentence, which was conjectured by Artin, is true in the p-adics for all large P. It's asymptotically true. Actually, Artin conjectured that it was always true, and that's false. That came later, but the correct statement is that it's asymptotically true. And well, I mean, I can tell you verbally what the sentence says. It says, for example, that any projective hypersurface of degree 5 in 25-dimensional projective space has a point in QP, has a QP rational point for large enough P compared to 5. And similarly for any other 5. Now, how did they prove this theorem. So it's, again, in some sense, it's an application of the same model existence theorem. What this theorem allows you to do is to give another possible construction of object as opposed to the usual topological constructions. And the reason that it's had so few applications is that once you've constructed a model in this way, you don't know how to prove anything about it. It just exists, but it doesn't carry a topology. The usual methods don't really work, and you don't really know how to analyze it. Okay, so how can you still prove something? How did they prove something before any techniques were any serious techniques were developed to analyze this type of object? Well, first of all, you have the notion of this is a theme of asymptotic things, which somehow we heard about throughout this talk, and I will also concentrate on it. So we have a notion of limits, which is associated with this logical stuff, and which is different than the notions of limits that you have arising from topology. So for instance, if you just take the points I over n between 0 and 1, like that, all the points for I equals 0 to n, so you get some kind of finite object, and what you might be used to is maybe thinking of it as a topological space, and you get the limit of compact spaces in the sense of Gromov, and you get the interval. Now in logic, you think of it as a structure. You see some relations between these points. Maybe you see the fact that every point has a successor, an immediate successor. For every point, there's another point, such that there are none in between. Okay? You see that sentence. It's true in each one of these finite structures, no matter how large n is, and therefore it will remain true in the model theoretic limit. So if this is mi, then to say that mi approaches m infinity is to say that any sigma true in almost all mi is true in m infinity. And the limit that you get will not at all look like that. It will have a first point, because all these models had a first point, and then there'll be a second and a third, and they'll somehow go like that, and there'll be a last point, and below it there'll be a penultimate point, and one just before that, and so on. It will have this kind of structure, and then you can impose a compactness requirement that makes it unique, and that will mean that there are a lot of points also in between. There will be some object like this. Of course, in this case, I took the limit of extremely simple structures, so I got a very simple object, and there's not much to say about it. But the point is this procedure implies in general, and for example, it applies to finite fields. When you take a lot of finite fields, well, if they all have the same characteristic, maybe you can take direct limit and get maybe an algebraically closed field or finite characteristic. But if they have different characteristics, you don't have any topological method to take the limit of them. But the model theoretic method is still going to apply, and you get a very interesting field that, well, today you can begin to analyze and to get back information about finite fields. Now, I think in this application, they still managed to get away without analyzing the limit at all. But what they did is the following thing. They looked at the limit of the sequence of p-adic fields, and it's something or other. Well, they analyzed it a little bit, but enough to show that it's the same as the limit of these fields, the power series fields over finite fields. So you see, once it's the same limit, you don't need to analyze that anymore. The Artin conjecture was already known for these fields, so therefore, since it's the same limit, it becomes known for these. There are more nice applications along with a few. I mean, there are few applications that you can get without having a new method of analyzing these new structures. There are a few. Well, to mention a very recent application, there's one by Thomas Scanlon about torsion points of Drinfeld modules. So you make up some polynomial which has the Frobenius in it. Maybe it's something like an operator of the form x goes to x to the p plus t times x, maybe, where t is transcendental. And you iterate, just for example, you iterate that polynomial, so you get higher and higher degrees, and you look at the kernels of these operators. And you ask how this set intersects curves, for example, and the answer is, well, it's going to have a finite intersection with the curve. This was conjectured by algebraic geometers. There's a well-known analogy there between Greenfield modules and elliptic curves, and this is an analog of what was called the Manin-Mumford conjecture for elliptic curves, but the only known proof is model theoretic. But I can't explain it to you yet because already it uses more than just the model existence theorem. It uses some model theoretic analysis that hopefully I'll explain. Maybe I'll be able to say something about it by the end of the talk. Okay. So I'm still, so now I go back and, now I'm going back to part 1 of the talk. And I have minus 5 minutes to finish that part, so I'll go a bit quickly. But here are some notions that you can say, which are clearly purely logical. They don't explicitly set out to look at geometry or anything. They just look at sentences and the relations between them, and they ask the most simple questions. So we said a theory is a bunch of sentences in some language. It's complete, well, the obvious thing, that every sentence is determined one way or the other. It's categorical. If a stronger thing holds, it actually has a unique model. There's a unique structure in the world up to isomorphism, for which it holds. Now, you need to qualify that to make sense of it. It turns out that, I mean, models are built out of sets. Ultimately, you have sets, and these sets have cardinalities. And these cardinalities are just irrelevant to logic, to this kind of logic that I'm talking about. So you cannot hope that sentences such as the parallel axiom or the negation of the parallel axiom will determine the number of points. You just have to fix the number of points in advance and to say, okay, but modulo that, any two structures are isomorphic. This notion makes sense. The notion of categoricity, of absolute categoricity doesn't, or at least it doesn't have an example. Now, the next one is going to sound different. In fact, it's exactly the same as completeness, but for morphisms between models instead of for the models themselves. But you can also state it syntactically. It says that every formula, anything that you can define, is equivalent to an existential one. The thing is that sometimes mathematicians are afraid of these existential quantifiers. For example, there's a paper by Van den Dries and De Neff that solves a conjecture of sphere about rationality of Poincare series. And the only thing there is that they're not afraid to look at definable sets that are defined with quantifiers. They look at these sets and they don't panic. They say, okay, we can still integrate over such sets. There's almost nothing there, but a lot of mathematicians come and say, well, what are these things? But the thing is that logicians are much more afraid of them than mathematicians are, because logicians know Gödel's theorem, and they know that all kinds of infinities are hiding behind these quantifiers if you can iterate them, if you seriously don't know how to eliminate them, if you get into a different world than what you thought you might be in. And model completeness means you're not in a different world, that you apply your logic to some geometry, and you're essentially still within that geometry. Maybe you have to project sets in order to get all, but you don't have to go any further than projections of sets. Right? We heard in various talks also how projections can be complicated, and if you have to iterate them to take projections and complements and then project again, you're totally away from the universe you thought you were in. So model completeness means you're not away from that. It turns out that the theorem of Abraham Robinson that, well, you see, if you write down a theory, you might ask whether it has a model completion, and it might not. But if there's a model complete theory that contains it and has the same universal axioms, then there's a unique one. So there's a canonical process for completing a theory. I'll give the example in a second. Yeah. Okay, so yeah, exactly. It'll come in the next slide, right? Okay, so there's a whole variety of theorems, each one of which has to be just proved individually. Does not use logic. Each one of these just uses the structure that it's talking about, which are modeled on a certain theorem of Tarski's, which says that the reals have a nice logic. The real algebraic geometry has a nice logic. Now, I wrote down 3 versions of that theorem viewed from different points. One point is the first point is that the reals have already been constructed. That's in version 1. We already assume that we know what the reals are, and we ask which sentences are true in the reals. And Tarski tells you, it's somewhat mysterious when you just say it that way, it's decidable. I can give you an algorithm to decide it. It turns out to be a doubly exponential algorithm when you look at it. but anyway, you can decide it theoretically. And exactly, it's very important to realize that this, well, it seems to be just about the real field, but it's about real algebraic geometry. Any question you want to ask about real algebraic varieties, after all, the point in the variety is given by finitely many coordinates. This is going to be an important word. And anything you want to ask about it, you want to ask about the singularities of it. If you think about it for a minute, you can define that set also. You want to say if they intersect, when you have the reals, let's say the minimal distance between two varieties, all these things are easily seen to be definable. So the real statement should be that elementary statements in real algebraic geometry are decidable. By elementary, it more or less means that you bound the degree of the varieties and the degree and the dimension of the variety in question, something like that. Well, it means something that you can state in the logic that I gave. Version 2, which sounds totally different, but it's absolutely the same theorem, just talks about semi-algebraic sets. A semi-algebraic set is something you can define using polynomials, equalities, and inequalities. And it just says that if you have such a set in R6 and you project it to R4, then it's again a set of the same nature. Of course, this immediately implies that every definable set is semi-algebraic, because if you think about the logical operations, well, they include conjunction, intersection, that's okay, and the only difficult one is projection, and this version tells you that you can do it. If you want to see, there's a beautiful presentation of the theorem from that point of view in Hermander's book, where he also explains the importance of this theorem and how some of the disjointness, the sociological disjointness between logic and geometry made, actually I'm not sure he explains this, but this was later explained to me, somehow created a delay in the time that this theorem was discovered. He uses it for various mathematical consequences, such as the curve selection theorem that I will not talk about. And also, well, okay. Another version, fine, and now we come to back to model completions. Don't think about the real structures. I'm not giving you the real field. I'm not giving you a topology. I'm not giving you a completion process. I'm just giving you the notion of an ordered field. So it's a very elementary notion. It's a field with an ordering on it, and it's compatible. But I haven't said anything about topology. Well, but I did say that, well, this theory does have a model completion. That's a statement. The unique model completion does exist. It turns out to be the theory of real closed fields. It exists, and therefore, well, okay, the theorems of real algebraic geometry are given to you by a non-topological process. It turns out that the canonical model you look at is not the reals. It contains all the reals, but also infinitesimals. But the theory is the same theory, and it gives you a non-topological way to construct this theory. And then the question becomes, okay, having done that, can you also prove anything about it? Given that all the methods of proof are usually topological. And okay, and the answer is for the reals, well, I think approximately no, right now. But for the question, having constructed the reals, or having constructed real algebraic geometry in a non-topological way, can you also prove things about it in a non-topological way? And for the complex numbers, the answer is yes. There's something called stability theory, which applies to certain things, which gives you a different approach to also proving things about the structure. For the reals, well, there's some beautiful things being developed now, but okay.
You can give elementary proof of integral compositor.
Well, I gave myself an easier task to just give a different proof of anything. But I wasn't talking about elementary proof. I was talking exactly, well, let me just for 1 second flash this. I will, yeah, okay, the useful part, it doesn't matter. It's a list. Each of these theorems requires an enormous amount of work of what kinds of geometry there is an analog of Tarski's theorem for. Maybe the important part is this green part here, namely the things for which there is no analog. And this includes, for example, it includes homology and cohomology theories. We do not know how to treat them in this way, even at the very basic level of just saying what the logic looks like. So it's on the wish list. I don't think it's necessarily infinitely far away, but yeah, it's something that does not exist. No global things are really understood at that level. The closest thing is maybe the algebraic integers, but they're still not quite global. They're all places but one in some sense. And we don't understand how to treat homology. However, well, okay, I mean, yeah. So this is supposed to be, so it's quite easy, right? I mean, when you're in a field which is in some sense looking at the same object but from behind, 100 years behind topology, it's very easy to have vision. You just say, okay, we're going to catch up. So I mean, this is an obvious research program to try to do analogs of Tarski's, still at the elementary level, to try to understand the elementary theory of such objects. Anyway, certain things do exist, but the point I was trying to make is that while the reals, I forgot the reals, no, here. The reals are here, and while you understand the elementary logic of it, there are almost no tools to deal with it afterwards. So even some of the beautiful theories that are being proved now about all minimal sets to the logicians who are here, sometimes they're being proved not in the saturated model, not in the canonical model of logic, but in the reals themselves. On the other hand, there was a massive and really beautiful theory developed, well, very largely by Shelach, originated by Morley, and with contributions by other people, that when it applies, gave us tools completely different from topology, but tools that can really say incisive things about certain structures. So the other thing for the future, of course, is to try to extend these theories to a larger domain of applicability. In the last 10 years, it has been done, extended a little bit, so we're able to deal with with asymptotic limits of finite fields, for example, which we weren't before. But, well, I'll explain more about this. Okay, so this was supposed to be the third topic of what is stability, how can we hope to extend it. But maybe I'll skip this. But I want to do the second subject first, because stability was not created with the idea of applying it to geometry. This came later, but the tools were created from a completely different point of view. And then people looked at the deepest things. This is maybe a confirmation of something that McPherson said this morning. People did try to explicitly look at geometry, things that already existed, and they got to a certain depth, but not very, very deep. They got to things like Tarski's theorem, and then you get it about something like real geometry, and then you just leave it there. On the other hand, people tried to look at intrinsic questions in logic, such as the question of categoricity, developed tools for that, and later it turned out that these tools can be turned around to actually shed light on geometric objects. So anyway, I mentioned the notion of categoricity, right, which you can state immediately after you have the notion of a theory. And the theorem I'd like to discuss is Zilber's theorem, which connects this notion to what I have here, to the notion of an asymptotic limit there. Of an asymptotic theory, the asymptotic theory of a class of structures. Okay. So what the theorem says is if you have a totally categorical theory that really describes its structures as well as it possibly could. Well, I just said Aleph 0 and Aleph 1, but there was an earlier theorem of Morley that said this implies every other possible size of an infinite set.
Would it have a unique model? Categorical means?
Yes, it has a unique countable model, and it has a unique model of any other size. Once you give me the set, there's a unique way up to isomorphism to put a structure on it, satisfying that theory. Yeah. So you have a theory which is totally categorical. Then, well, it's a theory of infinite structures. It's assumed to be a theory of infinite structures. But so it does not have, it's not a theory of finite structures, but asymptotically it is. Asymptotically what it's talking about is finite structures. So an example of that is the theory of infinite dimensional vector spaces over some, I don't know, the three-element field. It's talking about an infinite dimensional vector space, but obviously it's the asymptotic limit of the theory of n-dimensional vector spaces, each of which is finite. This theorem is deeply related to group theory. And that has to do with the application that I meant to talk about, the Flachland's program. But I don't know what you mean by an example. I mean, so the relation to group theory comes in the following way. The group is the automorphism group of the model in question. So the sequence of groups, GLN, or something like that, is connected to this. You know, I don't know. I'm not sure if I don't know if that answers the question, but well, maybe I'll have time to discuss it later. Okay, an extension of that is not only is it a limit in some way of finite structures, but I mean it has a neighborhood in the natural sentence topology which consists only of itself in finite structures. In other words, there's a finite set of axioms such that these axioms have only finite models plus the original intended model. And if you think about it, this implies there are only countably many objects in the world of that nature. So you see that it's a powerful theorem. It starts with this general notion of categoricity and shows you that you can make a list, at least theoretically. You can't in practice, but you can say a lot about them. Okay, so why am I saying this? I'm just mentioning internal relations between two notions in logic. But the reason I'm saying it is that there's no way to relate these notions like that. There's just no connection between being asymptotically finite and being categorical unless you go through structure theory for one of them, or both. And the structure theory explains what being totally categorical actually looks like. And suddenly you begin to see mathematics in the usual sense, mathematical structures in the usual sense. So roughly speaking, the theorem says that to be totally categorical is to say that a model of the theory is coordinatized by classical geometries of a certain type so far, over affine or projective geometries, over fixed finite fields. And there's a couple of more degenerate things that you have to say to make it correct and that I'm not going to mention. But let me explain the statement of the theorem. So before we started with the real numbers, we did what we usually do in mathematics. We took something like the real numbers, which is a really nice geometry, and then we made up manifolds from it, in this case, let's say real algebraic ones, and we said we can understand them with sentences. Now we're doing the opposite. We're starting with a theory which talks about something unknown, and we said, but they have to be coordinatized by one of a finite number of, one of a certain class of canonical geometries. We're going the other way. What I mean by coordinates, well, there's a certain sense in which to an element of a model of this theory, you can assign finitely many elements which are taken from one of these geometries, each one of which is taken from one of the geometries. Now, there is a difference from real algebraic manifolds, let's say, in that you have, to make this true, first of all, we have more than one geometry, right? But it's not just that you have two, or even that you have infinitely many sitting there and you can take mixed coordinates. You really have families of them and you have to take it into account. So it's possible that you have to choose the first coordinate, and then that chooses a point in a moduli space of other geometries, and then the second point will come from that. Okay. So, I mean, this is very familiar in geometry that sometimes, well, maybe there's, that there may be no global sections of a bundle or something like that. But here we have no section of any kind. You just have to give a point and then give the family of geometry. So if you go more into the details of this, you see that there are things that look like fiber bundles that explain the way this is happening. And that if you actually need more than one geometry, more than or a finite number of geometries to capture a point, then the only reason is that you have one geometry, and then you have a kind of bundle of other ones, but with automorphism group, with definable automorphism groups that gives obstruction to actually picking the next point. So the moral of this is that you just make the most basic definition in logic, and you immediately see some of the objects that are talked about, some classical geometries, a bit too special here, but still you see the beginning, and in something like fiber bundles, you start seeing these objects. This is this is something that needs to be said to make things correct, which I will ignore, to say what it means, but I want to explain this is. I said something is an affine geometry, and you just have to realize, how is it given? Well, there's a notion of an interpretation going on. What you actually were given in advance is a completely unknown structure. It's a very messy graph, maybe. And maybe you're being told, okay, no coordinatization necessary. It already is an affine geometry. But what that means is that there's some way to interpret the affine structure, and that there's nothing else. Everything else, the original graph structure, whatever, can be defined back in from the affine language. Now, there's nothing said about the length, for example, of the formulas that are necessary to go back and forth. And if I have time, I'll say something about that later, about methods for treating that.
This defined geometry can be identified as a algebraic geometry, such algebraic varieties?
Absolutely not. In the next slide, I'm going to get to algebraic geometry. Right now, we just have linear structure here. I mean, a bit less than linear structure.
You say that any categorical model, categorical theory can define model. Just take algebraic varieties.
Algebraic, so far I was talking about totally categorical, okay? Algebraic varieties are in fact categorical in power aleph1, but not aleph0. But I'm going to get to that in a minute. Wow. Well, yeah, okay, so the statement of the theorem shows you some connection with geometry. I'm not actually going to show you this. There was a little proof, I mean, a tiny part of the proof, which is kind of amusing, which forces you, well, you see, even after you know the structure theorem, the things are coordinatized by classical linear geometries, it still takes something to show asymptotic finiteness, and there's an amusing way in which this requires actually explicitly looking at the parallel axiom, using the fact that the geometries in the classification are really Euclidean, but so some of the original, but I will not do it, I think. In fact, there's some discussion of the proof which I will not do either, but I was planning to pause at a moment in the proof which was quite extraordinary and exists in all known proofs, namely you're classifying some objects that you know to be locally finite. This is because of the aleph0 categoricity assumption. Nevertheless, you're struggling with them and you keep running into the possibility of algebraic geometry being there. You have to first construct it under the existing assumptions and then say, well, okay, but it contradicts our assumptions, say it's not there. But it leads to a very strong feeling that under much weaker assumptions, logical assumptions, algebraic geometry becomes necessary. And in fact, Zilber formulated this conjecture. And in the 80s, this was somehow one of the organizing ideas in the area, saying that if you just look at aleph1 categoricity, so I've thrown away the categoricity in power aleph0, I'm keeping the categoricity in aleph1, and that's supposed to be just the same, that the theory in the same sense is coordinatized, well, by maybe linear type geometries, and maybe some degenerate things that I'm not mentioning, or the moment the complexity becomes more than linear algebra, it jumps to algebraic geometry. This was the idea, and this was the feeling that some parts of proofs gave, and somehow this would have settled all other conjectures in the area, which is natural, because what existed before was a method for coordinatizing things. But we had, it's like having a manifold and you know how to coordinatize it, but you don't know whether the coordinatizing objects are the reals or the complex. You don't know what the geometry is that coordinatizes it. This is what the situation we're in. This conjecture would have solved that.
Categorical doesn't apply unique model, not necessarily saturated model. Yeah, that were real is different, right?
Yeah, so like in Kazdan's talk, this question doesn't exist for me. I mean, so the theory, so it's like an algebraic variety. You can later fix the size of the model, but
real fields not there because they're not categorical.
Yeah, real field, absolutely, absolutely, absolutely. Real fields are not there, and the technology which is underlying these theorems just does not apply to them. And this is one of the goals for the future, to try to extend it. And since almost all mathematical questions involve many things, they don't just involve, well, I mean, usually they involve many different, various kinds of geometries. Right now, we have to be very lucky to hit on a question that we can solve with existing things. But if stability can be extended to include the other class, other geometries, then there can be more hope of doing things. Anyway, right, aleph1 categoricity is a property which is true for algebraically closed fields. It is not true for the real field. The reason is that the real numbers are unique with respect to natural properties, but topological properties. If you just write down purely finitary properties, they're not unique. You can have infinitesimal. Right. Yeah, well, so this would have implied a lot of things.
Is this a conjecture?
No. So, no, right. So it's
unique saturated model is not.
Sorry?
The saturated model is unique.
That's always true. So the saturated model, it's always unique once you know the complete theory. Yeah. Yeah. So this conjecture was actually settled both ways. So maybe I'll start with the true. Well, the true did require, and this is an admission of failure in some sense, it required a very small additional hypothesis. And the problem is not really with the additional hypothesis. It's somehow not really terrible to make it. But the reason it was terrible to make it is that it's stated in a different language. I mean, the additional hypothesis gives up and says, OK, I'm not just taking the definable sets. Among these, I'm going to single out something called closed sets, such as you have in Zariski geometry, and state one tiny requirement, but using that language. And having said that, the conjecture becomes true. There is this gap between linear algebra and algebraic geometry. You just say very, very minimal axioms, and it becomes true. Once this was found, analogs were found. There was a theorem, for example, of Petersil and Starchenko doing it for structures like the reals without additional assumptions. Because there the topology is already implicit. There's an analog for fields with automorphisms, which is used in this result of Scanlon that I cited. These results ended up having, together with the previous theory, they ended up having a lot of applications because you know how to coordinatize things, and then you know what they're being coordinatized by. And in applications, it's turned out that the topology did exist, and the additional assumptions were true. So maybe in the end, I'll say a bit more about that. Now, what happened slightly before it, this is a construction showing that in the original language, it was false. You can construct alpha-1 categorical structures that are coordinatized by something with a dimension theory which is not classical. And the question is still, what is the attitude that one should take to these objects? Personally, it's a new kind of thing, and the question is whether it's interesting enough to deserve the name of a new geometry. And I was quite pessimistic originally, whereas Zilber was, well, somewhat more optimistic. I mean, he felt, okay, I mean, he was sure that alpha-1 categoricity is a good assumption. If you find something else, it must be that that thing is important. And I thought it might be pathological. And I'm still not sure. I mean, it would be, of course, wonderful. The most wonderful thing that we could hope for is not just to shed a little more light on classical objects, but to find new ones. And I mean, I'm not sure. I'm not sure whether. So first of all, there's very little theory of them. They seem to be a mess so far. There are few dividing lines, and I don't think we know whether they have any real value or not. From time to time, we're beginning. Now that these things exist, we're beginning to run into them in a few places. So not into the whole. This construction turns out to fall into two parts. In the first part, you build something that has two-dimensional theories, one embedded in the other, which is something that model theory knows how to deal with very well. This was part of Shelach's theory. But you build one in which zero-dimensional things are not finite. And then you shrink them. Then you somehow shrink them to make the zero-dimensional things finite, and then you obtain really a theory of that type. Now, we haven't run in any kind of nature into something like that, but now that the first construction existed, you begin to notice it in a few existing places. So, for example, a few weeks ago, I ran into something, a question that was asked by someone called Koiran or something like that, who asked in a different language, what is that asymptotic theory? What is the limit in the model theoretic sense of the complex numbers with an additional structure, which is just a generic curve of degree d? Okay? So you take projective plane, you take a generic curve of degree d, all the coefficients are just transcendental, and you let d go to infinity, and you ask what is the theory of that? Okay, it turned out to be very, if you don't know the theory, it's hard to, you think, well, maybe it's very complicated, maybe it doesn't have a limit, a unique limit, but it has a unique limit, and it's exactly of type A. It's exactly one of these things that was found in the construction, but before, it's not actually alpha-1 categorical, it's a pre-alpha-1 categorical thing that hasn't been shrunk yet. So,
you need to have one of the theory when you look, the geometry of curve in degree goes up. You count curves of growing degree. Can it be related to that?
No, I can't relate it to that. I mean, first of all, because I don't really know this theory, and I don't expect that this is something very deep, but it's just an instance of, of an indication that maybe Zilber was right, and maybe it is a good thing to know about these. I don't know. I mean, this is one of the questions for the future. To what extent these will turn out to be important. Okay. Okay. So, yeah. So I have, well, okay, so I'm not going to talk about Lackland's program, which involved, perhaps this answer, I don't know if this is related, but the surprising thing about this alpha categoricity is, yes, it talks about finite objects in a way that makes you think of the classification of the finite simple groups, but it's ever so much weaker because you just see some things like the general linear groups, and you don't see symplectic and unitary and orthogonal. You don't see any of the other ones. And Lackland said, okay, but you can extend the theory so as to do it. And it has been done. And there are very fascinating questions there that relate finite, but using a classification of finite simple groups. Now, Zilber did it by hand without using it. And there are very fascinating questions about whether it can be removed, and if it cannot be removed, showing how it adds content, some added value to the classification. But
What kind of statement?
You want me to discuss it after all? It's so Zilber's theorem started from categoricity and then created a structure theory which implied local finiteness. Lackland, well, one starting point of the theory he said, okay, forget about categoricity, start with the assumption of local finiteness. So you have a model, a countable model, let's say, with very nice finite approximations, and then make a theory based on that. And you make a theory which is more general than categoricity, but it's still an extremely precise theory that shows you have a very limited class of infinite objects with such nice finite approximation. And then it gets turned around again. It starts with a class of finite structures and understands them by finding limits for them which are of that nature. The difficult thing about it...
Possible to imagine proving, say, there is a priori there is a finite number of exceptional simple groups. Whether such kind of things could be proved.
Well, I was saying, okay, I don't know about the entire classification, but there was an intermediate step towards that, which I was hoping to say something about. Even though the resolution of this program of Lackland used the classification, it couldn't use it in a simple-minded way. It had to first translate it to a list of, not to a list, to a collection of combinatorial model theoretic properties, such as the class of objects in question is not just given by a list, but you say, aha, but it's equivalent to a certain one, to a number of properties which are very well understood. Something like a general simplicity, which I wrote down before, is one of these properties. And therefore it makes it possible to imagine another proof because you don't, it makes it possible to imagine a non-inductive proof because you have to show that any finite structure with certain properties has certain, this is maybe too vague to make sense, but, well, okay. How many more minutes do I have now? 5, okay. So, so I really ought to mention stability because that's what makes absolutely everything works, and it's also the limiting line. Lackland's program was difficult because it breached the line of stability, and it's dared to imagine that this model theory can apply to things which are unstable. At the time, I mean, that was just a horrendous thought. Stability is a very, very strong assumption, but with this assumption, there was an enormous amount of technology developed, and some of the efforts that are being made now is to keep this technology while throwing away the assumption, or at least weakening it very much. Now, the assumption is very strong and it's model theoretic in nature. Namely, a model, you never look at one model. You always, this is somehow the idea that you always, if you have one infinite structure, then you also always have a bigger one. You always have these non-standard limits. Any countable sequence of points has a limit in some bigger structure. You always go to the saturation. And this is the enemy of topology, because you get a structure in which no countable sequence ever has a limit, because there will always be another point between it and the limit. Anyway, once you have this situation, you can look at, you have a model, you always look at a point outside it, somehow a limit, a point A star, which is in some sense a limit of points in the model. And you can ask, how does this point relate to the existing points in the model? If you have a possible relation phi, what is the set of all elements of the original, k tuples from the original model which relate to this new one. Now, if you take something like, well, if you take a model with no assumptions, you get extremely complicated sets. Even if this is a countable set, well, you get uncountably many possible subsets which are given in this form, and you don't know what to do with them. Stability says this set is always a definable set. So it's a very strong assumption, which is true, for example, in algebraic geometry. This has to do with a notion of a generic point and the property of unique behavior of generic points. This is something that exists in complex algebraic geometry, but not, for example, in real algebraic geometry. Okay, based on this notion, based on this idea, you have okay, let me just put up the next slide and then I'll stop. Okay, so based on this idea, you have a whole calculus of independence between different substructures, which has extraordinary strength. It's hard to imagine how much can be understood about a structure once you have this little notion. Well, since it's a notion of genericity, which exists in every branch of mathematics, maybe it's not that surprising. I thought to give an example of just one little lemma that can be done, that is assumed in this various work, which you normally don't talk about when you talk about some things. So what you can think of it as the analog of the Peter-Weil theorem about compact groups. Well, I mean, if you have a compact group, the Peter-Weil theorem tells you that it's basically over the real numbers. It is basically an object over the real numbers in the following sense. You have finite dimensional unitary groups, and maybe it doesn't embed into them, but you have enough embeddings to explain the group to you. Yeah? So you have this basic geometry, which you know what it should be. It's the reals. And the theorem says that the relation between G and this geometry is also group theoretical. And this is the difficulty in the proof. It's easy to find well, I mean, you first find functions into the reals, but then you somehow smooth them out. You do things to get group theoretic functions. Now, you're obviously going to need analogs of that when you analyze a structure which is not topological, if you want to say something about the groups in it. And well, if it's a stable group, I wanted to give the analog of that theorem and to show how, in some very vague way, the analogy of, in the Peter-Weil theorem, you integrate, you have a function, and you integrate, you make it more group theoretical by doing something like this. In the stable context, you have a formula which relates the group to some other geometry, but unknown. There's no field structure on it. And again, you don't integrate, but you define out, you take the definition which stability promised you of the interaction between a new element A outside the model, but viewed as translating the relation between this formula and the original group. And, well, I mean, you have a little bit more work, but using this, you get a kind of analog of Peter-Weil. Well, it's much easier than Peter-Weil, but it's also much more general. It tells you the relation between one of your groups, if the assumption holds, and an arbitrary and unknown geometry. So, okay, this has been, I'm certainly not going to have time to talk about that. This kind of thing has been extended for simple theories. Yeah, I guess I wanted to say, for example, we have absolutely no analog for valued fields, whereas we know, because geometers have worked on it, that such things exist. I mean, what you would expect is if you're taking a abelian variety over QP, that it should have a nice quotient over the residue field. That's one of those geometries involved. Well, this is something like semi-stable reduction. We know that it's there. From the model theory point of view, it should also have a nice homomorphism to a group defined over the residue group, over the value group, which is a strange notion geometrically. I don't think it's equally investigated, but the model theory ought to do it, and it ought to give explanations from a different point of view. Okay, should I ask for more time? Okay, I'll, what? Okay, so I don't know if it's important, but if I find the slide, I will just say how this little lemma is used in one of the recent families of applications.
I may ask you this question as a start of discussions.
In the discussion, okay.
So it just will happen in the discussion.
So I stop, yeah. Okay, so thank you very much.